Good day, hello everyone. My name is Olamotola Olawale, student ID 4425375. This presentation outlines my MSc research proposal titled Predicting Daily PM 2.5 Levels in London using Statistical Machine Learning Deep Learning Time Series Model. The main purpose of this study is to compare different forecasting approaches in order to identify which model is not only accurate but also practically suitable for predicting daily PM 2.5 levels in London. In this presentation, I will explain the research problem, research method, the data collection and processing, the technical modeling approach, and the ethical issues connected to the study. The focus on PM 2.5 is important because it is one of the most harmful forms of air pollution. Due to its very small particular size, it can penetrate deeply into the lungs and it is strongly associated with respiratory illness, cardiovascular disease, and wider public health risk. The issue is especially important in urban environments such as London, where daily PM 2.5 levels are influenced by multiple factors such as road traffic, weather condition, seasonal variation, and broader city activity. Although many forecasting models have been proposed, the problem is that findings are often difficult to compare fairly. Different studies use different cities, different predictor variables, different forecast horizon, and different validation method. Some focuses on hourly forecasting, while other focus on daily forecasting. Some use past PM 2.5 values, while others use meteorological and contextual variables as well. Because of these differences, it is not fully clear which model family is most appropriate for daily PM 2.5 forecasting in London when the comparison is carried out under one consistent framework. That is the gap that this proposed study aims to address. The aim of this study is to evaluate and compare selected statistical, machine learning, and deep learning time series model for predicting daily PM 2.5 levels in London in order to identify the most accurate, interpretable, practically suitable forecasting approach. To achieve this aim, this study has 5 main objectives. The first one is to identify suitable secondary datasets for daily PM 2.5 forecasting in London, including both pollutant and meteorological variables. The second is to preprocess and integrate those datasets into a coherent modeling dataset. The third is to develop and compare 4 fixed models: SARIMA, Random Forest, XGBoost, and LSTM. The fourth is to evaluate performance using standard forecasting metrics such as RMSE, MAE, and R-square. The fifth objective is to consider the legal, social, ethical, and professional issues associated with predictive air quality modeling. Together, this objective makes the project focused, realistic, and methodologically balanced. The study adopts a quantitative empirical research design using secondary time series data. This methodological choice is appropriate because this study is concerned with a measurable environment variable, which is daily PM 2.5 concentration, and it evaluates model performance using numerical indicators rather than opinions or experience. The research is also comparative in design because it does not examine one model in isolation. Instead, it compares different model families under the same general framework. More specifically, this study is deductive in the sense that it draws on existing forecasting literature and then tests whether the selected model performs differently when applied to the same prediction problem. This approach is suitable because it allows the research to remain systematic, evidence-based, and replicable, while also making it easier to assess the strengths and weaknesses of each model family in a consistent way. For data collection, the study will rely on secondary data sets rather than primary data. Daily PM2.5 concentration data will be obtained from relevant London or UK air quality monitoring sources. In addition, meteorological variables such as wind, wind speed, rainfall will be collected from appropriate weather repository. The reason for including meteorological variable is that PM2.5 concentration are not determined only by their own historical values. Weather conditions often influence pollutant accumulation, movement, and dispersion. So including this variable should improve the realism of the forecasting problem. After collection, the data will go through a structured preparation stage. This will include checking completeness, handling missing values, aligning data by dates, and converting them into a consistent daily time series format. This stage is very important because forecasting accuracy depends not only on the model itself, but also on data quality, future relevance, and correct temporal alignment. The technical approach is based on comparing four fixed models, each representing an important forecasting family. The first model, SARIMA, which serves as statistical baseline. It is useful for modeling structured temporal patterns such as trend and seasonality. It is also relatively interpretable. The second model, which is random forest, represents conventional machine learning. It is useful because it can capture non-linear relationship in structured data without requiring the stronger assumption using statistical model. The third one, which is XGBoost, is a boosted tree-based method. It is often strong in predictive tasks because it is sequential boosting process and its ability to model complex interaction efficiency. The last one, which is LSTM, it represents deep learning. LSTM is especially suitable for time series prediction because it can learn longer temporal dependency in sequential data. The reason for including this four model is to create a balanced comparison between interpretability, predictive flexibility, and computational complexity, rather than assuming that the most advanced model is automatically the best one. This study aims to compare them fairly under the same forecasting objective. The testing strategy is designed to ensure that the comparison is fair and appropriate for forecasting. Because this is a time series problem, the study will use a time-aware validation approach rather than random splitting. This is important because random split can cause information leakage from future observation into past training data, which would make the results less realistic. The model will be evaluated using RMSE, R-square. This metric provide a clear basis for comparing prediction, error, and overall model fit. However, the evaluation will not be based on accuracy alone. It will also consider interpretability, model stability, and practical suitability. This matters because the most accurate model is not always the most useful in real-world context. A model may achieve strong numerical performance, but still be difficult to explain, difficult to reproduce, or too computationally demanding for practical use. Therefore, comparison, we aim to judge not only which model performs best statistically, but which model is most defensible overall. There are also important limitation and ethical issues to acknowledge. One limitation concerns the use of secondary data. Public data sets may contain missing values, limited temporal coverage, or mismatched variables across sources. Another limitation is that model performance may depend heavily on the quality and representativeness of the available London data. There are also methodological limitations. More complex model, especially deep learning model, may improve prediction accuracy, but they may also reduce interpretability and be harder to reproduce consistency. In conclusion, the research proposed a quantitative comparative study of daily PM2.5 forecasting in London using statistical machine learning and deep learning model. Its main contribution is to provide a more balanced comparison under one framework while considering not only predictive accuracy, but also interpretability, reproducibility, and practical relevance. Thank you for listening.